I'm gonna start right away by solving this problem from Miriam and Craig. Before you watch this video, make sure that you have read the problem statement carefully with the hints. So this is the problem statement kind of from the book and the hints that I wrote. And kind of attempt your problem yourself and then let us solve it. So basically what is happening here is that this truck is moving in rectilinear motion. So all the points on the truck have the same velocity and acceleration. Basically you can choose your origin to be anywhere. And if you draw your position vector from the origin to any point on the truck, this is R1 to point 1, say, R2 to point 2. When you take the derivatives of R1 and R2, you're gonna get kind of the same velocities and the same accelerations. Maybe I should. Okay. So if I want to follow the 4 steps and I'm considering the whole truck, so consider the whole truck. Okay, we can consider it as a particle or we can draw a whole truck. Why can we consider it as a particle? Because, I mean, that's just what we've learned so far. And also, because it's in rectilinear motion, all the particles on the truck, they have the same position and the same, not the same position, the same velocity and the same acceleration. So consider the whole truck. We have R, well, I'm not sure, but V, it's gonna be, R depends on the point, but V is x dot ex. For sure, and y is and a is y double dot ex. X double dot ex. Okay, so this is the position, velocity, and acceleration. This is step 1. Step 2, we want to draw the free body diagram of the truck. I'm gonna draw the kind of truck as a truck, not as a particle. But if you were to draw it as a particle, that's not a problem for now. Okay, and we have kind of the front wheel is the important one, and the forces that are acting on it are the weights, W2 of the kind of back, W1 of the front, a normal force at the front, and the normal force at the back. You can combine both weights into one weight force like this, and both normals into one normal force like this, or you can keep them separate. It doesn't really matter for now. And we have a force here, attractive force of 20 kilonewtons between the driving wheels of the truck and the road. So this is the attractive force. I'm gonna call it F sub T, attractive force. Now, why did I draw it this way? Well, let us think a little bit. This truck is moving forward along positive EX. So if I look at the wheel, this is the front wheel of the truck. It's rotating with an angular velocity omega like this. Doesn't really matter what angular velocity is right now, but the point is that this point on the truck over here, the point that is touching the road, has a velocity in this direction. So that friction is going to oppose the relative velocity between the truck, between the wheel at this point and the road. So friction is going to oppose this velocity. We're going to talk more about friction next week, but friction is going to oppose this velocity, so friction is going to point like this. So this attractive force, which is the result of friction, points towards a positive EX to the right. Opposite to the motion, the relative motion of the wheel of the truck and the road at their contact point. Okay, so this is our free body diagram. We're not done yet. Let us prescribe the forces. So W1 is minus M1 G EY. Where here M1 is the mass of the first trailer, which is 10,000 kilograms, and M2 is the mass of the back trailer, which is 20,000 kilograms. Okay. W2 is minus M2 GEY. The normal forces, all we know is their direction. And then we have the attractive force. We know everything about it. Its magnitude is 20,000 newtons along EX. Okay, now we can do our step 3 and write F equals ma, the balance of linear momentum. So I'm just going to copy all the forces. I forgot the attractive force here. 20,000 EX is equal to the total mass of the system times the acceleration of the system, which is x double dot EX. I got that from step 1. So then if I want to calculate the acceleration of any part of the truck, including the drawbar, that's gonna be obtained by projecting this equation of motion, the balance of this balance of linear momentum about or along EX. So I'm gonna get that 20,000 is equal to m1 plus m2 x double dot, and you can calculate x double dot from this equation. And of course, the units in SI are meters per second squared. Okay, so then we got the acceleration of every point, basically any point on the truck. Next, we want to determine the tension in this drawbar. So the tension force in our first free body diagram was internal in the system, so it wasn't included in the free body diagram of the whole truck. But if I consider either the front truck or the back truck, then the tension force is going to become external to that system. So for example, let us consider the back truck. But if you were to do the same analysis to the front truck, you would get the same answer. So consider the back trailer. And let us do the 4 steps again. Again, the velocity and the acceleration of all the points on the truck are the same. And it's moving in rectilinear motion along EX. Now, if I only consider the back trailer, the forces acting on that are the weight of the back, the normal force at the back, and now the tension force from the drawbar. So if I were to look at the drawbar, this guy, it might be compressed or it might be extended. I do not know that yet. So I will write that the force T is some force along EX, and then we will figure out if T is positive or negative. And W2 and N2 have the same expressions as before. Okay, step 3, write the balance of linear momentum. F equals ma TEX minus m2 GEY plus n2 EY is m x double dot EX. And then that's the mass of the system, which is the back trailer. And then if I project this equation along EX, I'll get the tension force, the magnitude of the tension force actually, which is m2x double dot. So then you can write your tension force as whatever value you get along EX. Okay, that's it for this problem.